All right, we do not. All right, today you're going to take a look at a couple different things. First few problems you're going to see in the back is looking at chapters 2.3, which is the absolute value stuff. And so we will take a look at absolute values and distances. And so Ben, Liam, Dylan, focus, focus, focus. Okay? There's your message. Lee now knows I chewed you out, and it's going to get posted to YouTube.
I have sweet Hawaiian roll bread thing on my sandwich. It's so good.
Delicious.
Maybe you should start this recording over. Start it over.
That's probably a good idea.
No, it's going to be awesome when this gets posted.
All right.
We're going to have the whole, like, you guys getting moved out of the class, all recorded.
Like, what do you say, move down to class?
Like, just like permanently gone.
We can leave?
Like, I'll just like kick you guys out of class, lecture to everybody else who wants to learn, and then let you guys come back in and pretend to
You
learn.
said I didn't want to learn.
Your guys' behaviors and actions.
That's true.
Okay? Are we good now? Did we get a good message? All right. Now we're ready. Okay. So, number 66 and all the other ones from like 65 to 68. You're going to be taking a look at distance stuff. Okay? So, traffic jams. That's what we're going to look at right now. In a given day at a busy intersection, we're going to have an average of 726 cars per hour that goes through this intersection. During rush hour, it's going to be higher numbers. There's going to be more cars. During off hours, we'll have less cars. It never varies by more than 235 cars per hour from the average. And so we can look at this as kind of an absolute value type situation. But if we draw this as a picture, we can think about, on average, we'll have 726 cars per hour. Okay? During rush hour, we're going to have more. It never varies by more than 235 cars. So if we add 235 to the average, which gets us all the way up to 961. Okay, that would be the most amount of cars we would have in a given hour. And then during off hours, we'd have less traffic. Again, never varying by more than 235 from the average. Could take us all the way down to 491. So our average or our range of numbers here, traffic could be as light as 491 cars per hour or as heavy as 961 cars per hour. We could have anything in between. As far as identifying what that range is, we're going to look at 491 is less than or equal to our number of cars per hour, which will be less than or equal to 961. This is probably what we're most familiar with doing because this is the absolute values that we've been dealing with for multiple years. The more current stuff we've been doing is we can talk about how our cars per hour is some interval. So it's going to be part of that element of 491 to 961. Okay, so this is going to be either acceptable way of showing what that range is. Okay, so for the most part, we're just looking at that. And then if we needed to, eventually we'll learn how to put that into an equation. We can figure out, well, the actual number of people going in can be expressed by some absolute value equation where the number of cars is varying by that 235. Okay, next piece we're going to take a look at is the new material today. New material for the day, we're going to add two more parent graphs. First one will be this type of a graph. Anybody know what it is? Has asymptotes. Good, Lauren. It's a fraction, okay, which we're going to call rational functions. Y equals, most basic form is 1 over x. Good. All right, so the form 1 over x, if we look at that as a graph, we see that, yes, we do have these asymptotes. Okay, and so we'll have asymptotes at x equals 0 and y equals 0. Anybody know why the graph looks this way? Why is there an asymptote? Josh?
You can't have a number that equals 0 because you can't have a 1.
Good. So if x was 0, things freak out, right? Because we don't like dividing by 0. And so we can start to think about what actually happens before that. So if x becomes a really small number, let's call it 0.001. Okay? When that's a really small number, what happens to y? 1 divided by 0.001 is? Goes up. It's a really big number. Okay? So we end up with really big numbers as we approach 0. When we hit 0, things freak out because we don't like dividing by 0. That's where that asymptote comes in. And then when it goes to a negative 0.001, again, we get really big numbers, but they're going to be negative this time. So that's why you get those opposite tails that are headed towards infinity as we approach 0. Okay? How about the end behaviors? Why do those go to a horizontal asymptote? What happens when x gets really, really big? So let's say like 1,000,000. Y becomes extremely small. 1 over 1,000,000 is very small. Will I ever actually reach 0 though? No, because it's always 1 over some number. So we approach 0 but never quite hit it as we head towards the positive and negative infinities. So that's where the general parent graph comes from and why it behaves that way. We can take a look at these functions. We're going to see shifts also later today and how these behave. And so if we look at this, -1, that would probably, we'd anticipate that shift is towards the right one. Sure enough, we see that asymptote gets shifted 1 and up 2. So we see those things. We're going to describe the end behavior and then also describe what happens as we approach this vertical asymptote. So in our limit form, so we'll talk about in our limit form here. As we approach negative infinity, so as x approaches negative infinity, as this gets to be a really big number, what happens to our y value? What are we approaching as we head that direction? If we think about algebraically, 1 over a really, really big number is going to be 0, basically, right? So that kind of disappears. What am I approaching? 2. Okay, so that's why we end up with that asymptote there. Same idea as we approach the positive infinity. So as x approaches positive infinity, same idea. This turns into a very, very small number again, basically disappears. So we end up with 2 again. Okay? And when we see our limits going to the exact same destination, that kind of tells us, oh, hey, that's a horizontal asymptote. We're approaching 2, but we'll never quite get there. Okay, and that's where this limit comes in. The next piece is we'll talk about our limits as we approach a specific number. So as x approaches our vertical asymptote, which in this case is x equals 1, as we approach x equals 1, from the negative side, we'll put a little negative symbol up there. So as I'm approaching 1 this direction, we see our graph is headed down for forever. So this is going to approach negative infinity. Limit as x approaches 1 from the positive side. So as we're coming from this direction and we head up, everything's moving up as we go closer and closer to that spot. So this is going to head us towards a positive infinity. Okay, so now we have 4 tails. Do I need to split you 2 apart?
No, I'm trying to listen.
I know. Do I need to split you 2 apart?
No.
Okay. Ilya, back table, go.
What?
No, like the back desk.
Yeah, I know.
Yep.
There's only one back table.
Just plug in headphones or whatever you need to do, but just go in a zone and work. Okay, Jackie, now you can learn. You're welcome. Okay. So now you have 4 tails. You've got things that are approaching horizontal asymptotes, so as x goes towards infinities and negative infinities. And then you've got, as we approach this vertical asymptote, am I going up or down? So that'll be the first piece we look at, is trying to identify how these behaviors work with y equals 1 over x. The next graph we're going to take a look at is the second parent graph we'll look at today, which is what I like to call the volcano. Okay, so you get this up-up effect to it. Okay, this one is going to be y equals 1 over x squared. Okay, so again, this is going to behave the same way. When x is 0, we get that undefined moment, so you still have your asymptote. Okay? And as x gets really big, this turns into pretty much a 0, disappears. And so we'll end up with a similar shape, but because when we square negative numbers, they become positive, we end up staying in the first and second quadrant. Okay. So now, as we go to describe this, we can talk about end behaviors again. So we'll look at number 9. Okay, so limits as our x approaches negative infinity. As we head towards forever that direction. Okay, this gets really big, so it turns into a 0. Okay, and we're left with 1. So we're approaching a positive 1, which hopefully makes sense because we're shifting up. As we approach the positive infinity, same situation. X gets really, really large. Okay, so that basically turns into a 0. And we'll approach 1 again. So there's our horizontal asymptote. We're approaching 1, both positive and negative infinities. And then as x approaches our vertical asymptote, same concept. We want to know when are we going to divide by 0. So if we solve for that bottom piece, we're looking at x equals -2. So as x approaches that -2, from the negative side, so as we come from this direction, we see that we're disappearing into the positive infinities. So this will equal a positive infinity. And limit as we approach our asymptote from the positive end, -2, from the positive end, we'll see again this is going to take off into the positive infinity. And so our tails are up at that vertical asymptote. Okay, so we'll have 4 tails we're going to talk about with our limit system. Questions on any of that stuff?
So the first, the 2 limits on the left, those are the end behaviors.
Those are the end behaviors as x gets infinitely large or small. And in this case, we're starting to approach horizontal asymptotes
And then the 2 on the right are the
as we approach our
negative.
interior asymptote. So with 1 over x, we get the opposite behaviors. With x squared, we get similar behaviors. So the horizontal asymptote is this piece.
So it's the horizontal and the end behavior? That's the same one?
Correct. So we see that our end behaviors approach the horizontal asymptote. So your horizontal asymptote, because we didn't actually answer that question. Sorry, name the horizontal asymptote. So naming the horizontal asymptote would be y equals 1. So that is our horizontal asymptote. Okay? And then our vertical asymptote would be x equals -2. And hopefully that makes sense because we know that our equations, y equals a number is a horizontal line and x equals a number is a vertical line. Okay? All right. Next piece we're going to take a look at is they will actually give you a graph and just have you sketch it. So we're going to go back to the idea of how do these shifts apply. And just like the other 6 functions we looked at the other day, the same shifts are going to apply, up, down, left, and right. Okay, so we're going to sketch these. I'm going to actually give you one that's a little bit more complicated, just so we're familiar with it. So y equals 1 over x minus 2 squared plus 3. Okay? What's going to happen to that graph? First of all, what's its parent graph? Go So y equals 1 over x squared. So this will kind of have that volcano look to it. Okay, the up effect. And then we're going to shift left, right, up, and down. Where are we going? This tells us right 2 and up 3. Excellent. So when we go to sketch this graph, normally our asymptotes are at 0s and 0. We're going to shift those asymptotes to the right 2. And then we're going to shift it up 3. So now I have my new asymptotes. And then I know that it behaves like an x squared function. So we've got the volcano kind of a look to it. And there's our sketch. Okay, so now our shifts left and right essentially are going to move those two asymptotes we've got. They're going to shift the asymptotes, and then we can still fit it with our shapes. Okay, it's going to ask for the x and y intercepts if they exist. In this particular case, if I plugged it in x equals 0 and solve for a y-intercept, so y equals 1 over 0 for x minus 2 squared plus 3 squared plus 3. So this is going to equal 1 over negative 2 squared is 1/4. So 3 and a fourth is 13 fourths. So y equals 13 fourths. Okay, so there's our y-intercept at 0. 13 fourths. And then if I plugged in y equals 0, we should be able to find our x-intercept. Okay? So if I plugged in y equals 0, now we end up with 0 equals 1 over our x minus 2 squared plus 3. Okay? So we'll end up with negative 3 equals 1 over squared. And as we keep working through this, what we're going to find out is x minus 2 squared equals negative 1/3. How do I undo that on the next step? X minus 2 squared equals negative 1/3. What would we do? Take the square root. When we take the square root of a negative number, what happens? I. We have imaginary numbers, right? So in a real coordinate plane, do we have any x-intercepts? No. So this ends up not having any real solutions. So no real solutions. Okay? And because of that, we don't end up with an x-intercept. And as we look in our graph, that makes sense because we don't actually cross the x-axis. Okay? So mathematically, that's how that works out and why you don't have any x-intercepts. Okay? Next piece we'll have is we're going to give you a graph and then ask you to write the equation for it. Okay, so when we look at that, let's do number 28. What's our parent graph? Y equals 1 over x squared. Good. It's reflected across the x-axis, so what are we doing to it? Multiplying it by a negative. Good. So it'll have some sort of a negative piece to it. Okay, and then we have shifted it left 2 and up 2. Okay, so when we go to apply that, we end up with y equals negative 1 over x plus 2 squared plus 2. And then we end up with our equation for that function. Okay, so look at the reflections, look at the shifts left, right, up, and down, and then we can apply all that piece and we can actually come up with an equation. Okay, and then the very last piece we'll look at today is just identifying that no matter what your parent function is, no matter how weird it gets, you can still apply your shifts to it. And so we're going to look at something that's got a really weird exponent, such as number 60. And so if I look at g of x being x to the 8/7, okay, I don't necessarily know what that is. Okay, it's x to the 8th to the 7th root. Right, it's going to be kind of a weird looking thing. But then I know that x minus 3 to the 8/7 plus 2, what am I doing? Right 3 and up 2. Okay? Our shifts are universal. It applies to any equations we work with. So find your parent graph and then just shift left or right, up and down, and we can identify those. Feeling good?